All right, so for the physics principles present in our MTC, the first one we have obviously is springs, um, as a mousetrap is powered by a spring, and this is therefore powering our whole car. And the spring formula, potential energy of a spring is equivalent to the spring constant times the displacement of the spring squared. Explains why we have a rule that we cannot bend the mousetrap past a 180-degree angle, as this would store more potential energy and give that group an advantage. So that's why that rule is in place. And then the next principle we have is the conservation of energy. This whole project revolved around the conservation of energy, as when the spring is pulled back, we gain potential energy, and when it is released, that potential energy is converted to kinetic energy, which is our car moving. And the last principle we have is torque. When we pull the arm of the mousetrap, torque is created as the line of action does not cross the center of rotation. All right, so for the physics principles that we utilized in the production of our car, the main one we used was torque, and the first place where this shows up is in the actual movement of the mousetrap. Um, since each group received the same mousetrap, we have the same amount of torque to work with, and this is represented by the formula torque is equivalent to the length of the arm times the force times sine theta, and theta is the angle of the arm to the direction of the force. Since the direction of the force the arm applied was in a circular motion, it means that sine theta would be pretty much the same for all groups using a string to create movement. So the two factors that we could play with were the length of the arm and the force exerted by the arm. Since this is not a speed competition, we don't really care much about the force as long as it stays high enough to overcome the initial friction and the moving friction. So we maximize the length of the arm, which pulled a larger amount of string, which translated to a larger amount of rotations as the string was wrapped around an axle. The next place where we utilized this torque formula was in the wheels. In this case, however, the torque was the axle spinning because the string was being pulled, and the length of the arm was actually just the radius of the wheel. Once again, we applied the same logic that we don't need a really high force because we don't need it to be fast. So we made our wheels as large as we possibly could. And larger wheels mean they have a greater circumference, and a greater circumference means we have more distance traveled per rotation of the axle, so we can maximize our distance traveled. And then together with this long arm length and large wheel size, we were able to get both a lot of rotations of the axle and a lot of distance per rotation, which meant we were able to cross the whole distance, even if it did go at a very slow pace.
Hi, it's me, Christian, obviously, and I was just going to run you through the materials that we used. So basically, here we have a list of all the stuff that we used. The copper rod was used as the extension for our lever, and then also as our axles in order to reduce the amount of friction rubbing on the plastic. We had plastic plates instead of paper because we needed them not to bend, and our contraption was quite heavy, and so paper wasn't exactly going to work. And then we used the plastic filament, which was the base of our car, and then also these little things to prevent our wheels from sliding and tilting. And then as for the construction, it was actually really simple. Basically, all we did was we just 3D modeled all of our pieces, placing them with the exact dimensions and everything, and then we put it into a 3D printer, which essentially just takes those digital designs and turns them into real ones using the exact same measurements. It takes like about 4, 5, or 12 hours, depending on how big you end up printing. But yeah, that was our construction process. And now for just a quick rundown through the transfer of energy. Essentially, what we had was we had a transfer of potential energy to kinetic energy. So as we pushed back the lever on the mousetrap, that essentially stored a large amount of potential energy, which then, when we released it in the mousetrap, the spring tried to return back to its neutral position or its original position. That potential energy got transferred to kinetic energy, which then, through the string, got moved to our axles, which rotated the wheels, which ended up causing our motion. And then there was one last energy transfer, which was at the very end when our mousetrap slammed into the wall of the tennis court, which it ended up sucking in all the kinetic energy from the car and transferring it across the entire wall, which of course isn't going to move it because the car didn't have enough energy to do that.